Okay. Hi, everybody. I'm Adam Forsyth. I'm a group engineering lead and the community lead at Braintree, which means I do both software design and development, and I also help sponsor events like this. As you saw, Braintree is a sponsor. Braintree is the name of a town in Massachusetts where President John Adams was born. And that is, our founder was a fan of him, and that's why he called the company Braintree. It has nothing to do with education or trees. Yeah, so this talk is called Python for Home Ec, and I believe that the previous version of this talk I gave is already up on my GitHub, so this is just a slightly altered version of that talk. I gave it at not ChiPy. So if you look at the Wikipedia page for Home Ec, this is what comes up. It's a little bit of a stereotype, a little aggressive maybe, not my definition of Home Ec. Home Ec is actually defined as the profession and field of study that deals with the economics and management of the home and community. So a little bit broader than anonymous 1950s person in the kitchen. So I'm going to walk you through two different problems that show you how to do things around your house more efficiently with Python. And hopefully it'll really serve to remind you that you can use programming to solve problems in your everyday life and teach you how to think about problems in a way that lets you use a computer to help you solve them. So this is Jonathan Lukens, my coworker at Braintree. He is an engineer, software engineer. He's also a farmer. He has a farm in Connecticut on which he lives. And he's a do-it-yourselfer, as you can see by the fact that his desk is in his wood shop. And he is the person who inspired this talk. The problems I'm going to talk about are actual problems that he had around the house in fall and winter of, 2015, I guess, a little while ago now. And they're real problems that I helped him solve using Python. So the first problem I'm going to talk about is the design and construction of this countertop that you see in the picture. It's a butcher block countertop, which means it's made up of many small pieces of wood laid along each other. As you can see, this countertop is L-shaped, and it's joined diagonally. So every piece of wood that you see in that picture is a different length. And so that means that it was a really hard problem for Jonathan to figure out, given the pieces of wood he already had, how he could cut all those lengths he needed out of those pieces of scrap wood so he didn't have to spend any money. So first of all, a little nomenclature. We're going to call the boards you start with before you've cut anything boards, and the pieces that you end up with cuts, or just pieces. So in this example, you've got two boards, one 7 feet long and one 5 feet long, and you've got 4 cuts that you need to make, 2 4-foot, a 3-foot, and a 1-foot cut. And so you can see that if you try and make the cuts in bad places, if you try and cut the 3-foot cut out of the 5-foot piece of wood, then you're not really left with enough wood left over to make all the cuts you need. But if you start out and you place the cuts smart on those two pieces, on those two boards, you're going to actually have enough wood to make all 4 cuts out of just those 2 boards. So that's the problem we're talking about, is how to pack these cuts into those boards as efficiently as possible. So let's figure out an algorithm. The goal is to find places for the biggest cuts, the ones you're least likely to be able to make. So if you start out trying to make the biggest cut first from the smallest piece of wood, and then you make the next biggest cut wherever it'll fit, but trying from the smallest piece of wood and then going bigger, you end up filling them efficiently. You cut 4 feet off the 5-foot board, then 4 feet off the 7-foot board, leaving you with a 3-foot piece and a 1-foot piece, which is exactly what you need. So if we look at the countertop, though, it's a little bit of a different story. We don't have to make just a few cuts here. We actually have to make 64 cuts of all different lengths. And Jonathan didn't have just 2 boards or 3 boards. He had 35 boards, which were 3 different lengths. And it actually will become important later that although there were many boards, they were only of a few different lengths. You'll find out why that's good later. And there's actually one thing I mentioned so far. How many people here have used saws to cut boards up before? So Have you ever, you measure the board, you draw the line, you make the cut, and then the board is too short? Because when you cut the wood, you lose some length. Does anyone know what that is called? What is that? Kerf. The kerf. That's right. So what we didn't account for in our example, but you actually do have to account for in real life, is the kerf. So because we have so many different cuts and so many different boards, and the boards are of different lengths, and you have to account for the kerf, you can see why we don't want to solve this problem by hand. We'd really much, much rather let the computer do it for us. So here's the code. It's less than 20 lines in Python. If you write it in Ruby, it's just over 20 lines. Yeah, so we're going to walk through this code, but don't worry if you don't get every single bit. I'm going to move kind of fast. I'm not going to explain everything super clearly. So don't be surprised if you need to look at this again on GitHub or in the video later. Yeah. So we call this method greedy approximation. And the reason it's greedy is because we start by cutting as much as possible out of as little as possible. You want to make the biggest cut out of the smallest piece of wood is the general idea. Is what we saw in the example. So the first thing we do at the very beginning is we pass in the lengths of the different cuts we need. So in our example, that was 4, 4, 3, and 1. The lengths of the boards we have in our example, that was 7 and 4. And the size of the kerf, which is probably something like 1/8 of an inch or something like that. So 0.0125. Sorry, 0.125. Yeah, so, and then you sort of add some, you take your lists of cuts and your lists of boards and you add some metadata. So you sort the cuts in order from biggest to smallest because you want to make those big cuts first. And in addition to storing the length of the cut you need to make, you also want to track, have I actually made this cut yet or not? Have I found a place to cut out this piece? And then you do a similar thing for the boards. You track the length of the boards, how much of the board you've used up to make cuts, and which specific cuts you've made out of that board. And that's really the output of this function, is the list of what cuts you made out of what board, because that's what lets you go take your saw and actually do it without having to think about it too much. So the next thing you do is we go through all the cuts, and for each cut we go through all the boards. So we're going through the cuts in order from biggest to smallest. If the board has some length left to be used, if the board has already had a cut made out of it, we know we have lost some length to the kerf. So when we look at how much is left, we have to take into account that kerf from that previous cut. For the very first cut, we haven't lost any kerf yet. Right? So you don't need to. If you need to make a 54-inch cut from a 54-inch board, you don't actually cut anything. So you don't lose anything to the kerf. So you get one cut essentially free from every board without having to account for the kerf. Did you have a question?
Yeah, I was going to ask how you're going to deal with the principalist problem with respect to the kerf, but I guess this addresses that.
Yes, that's exactly what we're doing here. We're ignoring the kerf from the very first cut so that we don't have to, because it doesn't matter. If you only have one cut to make, you don't have to account for the kerf. Yep. So, and we know if we've made a cut yet. If we've used any from the board, we know that a cut has already been made. So we have to account for the kerf. Yeah. So now if we check if the length, the original length of the board minus the amount we've used so far is greater than that length that we need to be able to cut from it. And if it is, we mark that we found a place to make this cut. We mark that the board has we have used that length from the board, and we append that specific cut to the length of cuts that you made from this board. And the reason we track whether or not you found a place to make the cut, even though you're only making one pass to the cuts, is so at the end, it's easy to see, oh, we couldn't find anywhere to make this cut and this cut and this cut. We never found a place to make them. So that's the only time that you need the found thing is at the very end, after because you're only making one pass to the cuts, so you don't need it while you're doing it. And again, like if you're able to find a place to make this cut, you don't need to look at the rest of the boards. You've made the cut. You can move on to the next cut. You don't have to look at the rest of the boards. So we break out of the inner loop. So some of you may have noticed I missed something. Can anybody spot what's missing from this line that I mentioned in our example? No? We're assuming everything is on a square. The kerf, we don't need to take into account until we actually make the cut. So what we're missing here is I said that we sort the boards in a certain way when I showed the example, but actually here I didn't sort the boards. It turns out that sorting the boards in that specific way will guarantee you 50% fill. You'll always use at least 50% of your wood, but it doesn't make it optimal. It just means that it'll always at least beat 50%. So in this case, if you were to sort those boards in the way I said in the example, from smallest to largest, you're actually going to find 17 cuts you can't make because the numbers just don't line up right. But if you, in this case, leave them unsorted, but basically if you do them largest to smallest, you're actually able to find places to make every cut but one. And that's not inherent to the problem. That just happens to be how these lengths line up. That flipping away the way you sort them is actually better in this case. So remember, we're solving a real-world problem here. It's not a computer science theoretical thing. We're just making a countertop. So this is actually great. We found a way to make all these cuts but one, and we can just use 2 small pieces of wood to make up that 1 extra cut. That's just 1 piece made from 2 smaller ones. That's great. That's really efficient. We're super happy with that. So we actually could just stop right here. We're done, right? We've got our countertop ready to be made. And this is actually how it ended up being made. But if you take advantage of one special feature of this problem, that all the boards Jonathan had were only 3 different lengths, you can actually do even better. So we talked about if you sort the boards smallest, middle, largest. We talked about if you sort them largest, middle, smallest. But actually, if you sort them smallest, then largest, then the middle length, you can actually make every single cut out of those boards. So it turns out that taking advantage of like special features of your problem, like all of your boards being just 3 lengths, and doing some manual work, sometimes lets you extract even better results than you would by a sort of a little more naive algorithm or without the help of a human brain. So yeah, a little manual work can really help a lot. So let's talk about theory for a minute. We are going to step back into a little bit of theoretical computer science here. Does anybody know what I'm about to talk about based on this picture? That's right. Yeah, the knapsack problem. So the knapsack problem is the general type of problem that this falls into. You have a backpack that can hold 15 kilograms, and you have a bunch of items, and each of those items has a value to you, and it has a weight. And so your goal here is to pack as much value as possible into that knapsack without exceeding that 15 kilogram limit. So how to pick those items most efficiently to fill that backpack is the knapsack problem, and is basically what we're doing here. So if we wanted to apply our greedy approximation algorithm to the problem, right, we only have length, right? We don't have both weight and value. So if you wanted to apply this algorithm, you would take the ratio of the weight and value and then apply this solution to that. And that does give you, it is an algorithm you can use to solve the knapsack problem. It's generally not going to give you an optimal output, but it will give you better than random chance. It will tend to give you at least a 50% efficient solution. Yeah. So there's lots of different versions of the knapsack problem. One of them is called the subset sum problem. And this XKCD comic is an example of that. It's a picture of several people at a restaurant, and they tell the waiter they want to order exactly $15.05 of food and expect the waiter to just figure out what appetizers and other foods add up to that. And I believe there's actually a typo in this comic. There's actually 2 different things, 2 different combinations that add up to exactly that. So they didn't well specify their problem. But I think that if you just get like 8 mixed fruits or whatever, it adds up to that amount. Or there's some other more complicated solution. But anyway, so the subset sum problem is a type of knapsack problem where you have to exactly hit that weight limit or that amount of money. You have to exactly hit it, not just stay under it. And weight and value are both the same here. There's only one number again, like in our problem. So on the other hand, there's another problem called the stock cutting problem. And in this one, you basically have multiple knapsacks. You have a whole bunch of knapsacks, and and your value is, again, equal to your weight. You want to maximize how much of them you use up, but you don't have to use exactly the whole thing. So imagine you're a commercial paper company, and you make giant rolls of paper, and you have a whole bunch of them, and you have a lot of different smaller pieces of paper you have to cut out of those big rolls. That is shown up here on the screen, and that is the stock cutting problem. But in paper or in sheet metal, for example, the problem is two-dimensional, right? You have length and width. But in our problem, you only have length, and that's just because it's a one-dimensional. But it's still the stock cutting problem. You have a whole bunch of boards. You have to cut as much of them. You have to cut stuff out of them. You don't have to use the whole board. It's the stock cutting problem, except in one dimension. And this is an important problem in lots of industries, like paper and sheet metal making. And it's generally solved using proprietary commercial software. So this is an actual real application of some of these algorithms. So why is this important to us as software engineers? What is an example you might actually run into at work of having to solve this kind of problem? Yeah, so imagine you have two physical servers, one with 5 gigs of RAM and one with 7 gigs of RAM. And you need to spin up four VMs, and they need 4 gigs of RAM, 4 gigs of RAM, 3 gigs of RAM, and 1 gig of RAM. If you put the 3 and the 1 on the 3 gig of RAM and the 1 gig of RAM one on the smaller server that only has 5 gigs, you're not going to have space to fit both of the 4 gig servers. Yeah, OK, it's a made-up example. But so that's basically what you want to do here. This isn't a way to pack those VMs onto those servers to make efficient resource usage. Now, in this picture, again, it's just one-dimensional, right? You just have RAM. But in reality, of course, you have RAM and CPUs and IOPS, or input-output capacity on the hard drives. You have multi-dimensions. So it is really a fairly traditional industrial stock cutting problem, except I know, at least where I work, we don't use any fancy software to solve it, and therefore probably do it very inefficiently. Yeah. So if you're interested in learning more about the knapsack problem, Wikipedia is a perfectly good place to start. It has examples of algorithms. It has discussion about it and its historical significance. It talks about optimization problems in general. It's a good place to start. So I'm going to take a quick breath here and have a sip of my melting ice before I move on to the second problem. Cool. So the second problem that Jonathan had relates to his pantry. Unfortunately, unlike the picture of the countertop, this is just a clip art I pulled off the internet. This isn't actually his pantry. His basement is much dirtier and darker than this would indicate. I've been there, yeah. But like in this picture, Jonathan has many different kinds of preserves in his basement because he's a farmer. So he preserves a lot of stuff for the winter. His family eats them like the whole winter all the way until late spring when they start getting fresh produce again. And he wants to sort the preserves so that through the winter, they have the maximum variety over the course of this time. They don't want to eat all of the strawberries first and then eat all of the rhubarb and then eat all of whatever. They want to spread it out. So it seems kind of simple, but it's actually a little bit complicated. And I'll talk to you about why. So from here on out, I may call these jars or preserves or something like that, but I'm just going to represent them as pixel art. So if you have, just say, 3 different kinds of preserves, and you have about the same number of each, right? You have 3 of each in this case. You can just sort of evenly space them out, and you're going to have a lot of variety, right? In the first third, you have 1 of each. In the middle third, you have 1 of each. And in the last third, you have 1 of each. And none of them are ever one after another. It works out great. You've got lots of variety. Cool. But what if you've got way more of one kind of jar than of the others? So in this case, you have a lot of red jars. If you try and just sort of equally space out the blue ones or the red ones, you're going to end up clumping the other ones together. And so you don't want to have red jam 2 days in a row, because you're already going to have red jam almost every other day. So you really don't want to make it any worse than it already is variety-wise. So if we evenly space red, no color is twice in a row. But the blue isn't perfectly evenly spaced, but this is still pretty good. You're still getting pretty much as much variety as you can get here without clumping anything closer together. So we need a solution that when there are 2 different kinds of jars and they both can't be equally spaced, because in this case, if we wanted the blues to be equally spaced, we have to swap the blue and the middle red. So they can't both be perfect here. We want something that's an algorithm that's going to put the most common jar in that place where they both want to be, so that the most common one is the most equally spaced. Because we don't care if the blue is a little bit off here, because the red is the one that would be bunched up if we weren't really careful. So my first thought when solving this was, what if we basically put the most common ones equally spaced on the shelf, and then take the next most common ones and put them equally spaced, and then sort of take the least common ones and stick them in the middle. Unfortunately, then you end up with something like this. And you can sort of move the greens around wherever you want, but this is still going to kind of have either two green ones together in the middle, or it's going to have red ones really close together in the middle, and it's not going to end up evenly spaced. So this strategy doesn't really work. It leaves the least common ones, like green, bunched together wherever there happen to be space left, rather than giving you a good chance of having even the least common ones, like green, spaced out some. Right? If I'm only going to have pairs twice in 6 months, I don't want it to be Wednesday and Thursday of next week. I want them to be spaced out some. So how do we avoid this? What if instead of putting the jars on the shelf equally spaced and then sticking ones in the gaps, what if instead we put them all next to each other and then spread them out and stick ones in between? So if we put all the red ones on the shelf, then we spread them out, put the blue ones in between them, spread them out some more, and stick the green ones in between, it looks pretty good, except again, you've ended up with the red ones clumped together in the middle. Just because they're the most common, they're going to tend to stay more clumped together. So it still doesn't really solve our problem. So if we try the same general idea, but we start from the least common this time, which seems a little counterintuitive because it's the most common ones that we care about the most, you start with the green ones, and then you stick the blue ones in, and oh, it really doesn't look that good, right? The blue ones are kind of clumped together, the green ones aren't centered. But then when you add the red ones, you end up with the red ones perfectly spaced. The green ones ended up with a blue and a red one in between them, so they're pretty spaced out. And the blue ones are pretty close to even. So what you've done here is figure out an algorithm that lets you not take most advantage of spacing out the red ones by putting them on exactly where you want them last, while still tending to spread apart the green ones that are the least common. So this seems like a good algorithm. And this code is really short, shorter even than the last one. And again, I'm going to go through it line by line, but don't worry if you get every piece. There's a little bit of slightly tricky math in here just to get out loud without having a pen and paper of your own. So feel free to take a look online or in the video, on GitHub or in the video afterwards. So first of all, here's the actual data set for this problem, the actual jars that were in Jonathan's pantry in winter 2016. Tomatillo caper soup, he had 3 jars. Spicy marinara, he had 5 jars, et cetera, et cetera. But then if you look on the next line from the bottom, he actually had 20 jars of salsa verde. So that's your outlier where you really want to try and space them out really evenly, because I love salsa verde, and it's like the one thing I always like have a jar of at home, but except it always gets moldy before I finish it. But you don't want it every single day for like 2 months. You want to spread it out over 6. So the first thing we do is we turn the hash, the dictionary of items, into a sorted list of number name pairs. So this is going to give us the least common ones first, followed by the next least common, all the way down to the most common. And then we're going to create a new list and use that as our shelf. And of course, it starts empty because as of yet, we haven't put any jars on the shelf. And then what we do is we go through our list of jars from least common to most common, like we figured out in our toy example. And we figure out how many gaps there are going to be. So for the very first jar, there's going to be you're going to have 2 gaps, right? You have 3 jars. There's 2 gaps in between those 3. And so far, there's nothing on the shelf, so the shelf is empty. So the spacing between the jars is going to be 0, the jars on the shelf, divided by 2, divided by the number of gaps. So you're going to have no space between them, and you're just going to stick all 3 jars on the shelf for your very first one, because there's nothing to put in between. But as you go down, the gaps is going to gradually increase because you're putting on larger and larger groups of jars at once, because you started from your least common, goes to your most common. And the jars on the shelf is going to increase also because you keep putting jars on. So gradually this spacing is going to increase above 0, but since both the numerator and denominator are increasing, it's not going to get super high because the jars on the shelf and the number of gaps are both going to go up over time, though the jars on the shelf will tend to go up a little faster, so it will tend to grow slowly. So once you figure out this spacing that you want between each jar, you can actually take your shelf and insert the jars into it periodically. So for each jar in your number of jars, so for the first one, 3, and for the last one, 20, you're going to, for each of those numbers, 0, 1, and 2, from 0 up to less than 3, you're going to figure out the position on the shelf where you want to insert the jar. And this is where it gets a little bit tricky. You multiply the spacing, which could be a floating point number. It doesn't have to be an integer. It could be a fraction. By the number of jar you're inserting, and you round it to the nearest integer, and then you add which jar you're at. Because after I've already added one jar to the shelf, that's going to push all the jars to the right over by 1. So if I want to correctly space my next jar, I have to account for the fact that everything's been pushed over 1. So that's why that I is added on again at the end. And you just insert into the shelf, which is just an array, a list, at that position, the jar of that name. And if you notice something maybe a little bit wrong with that last line, don't say it right now. Just think about it for a second, give it a chance to look, and we'll talk about it in a minute. So the solution works pretty well with a relatively small number of jars. But did anybody spot the inefficiency with that last line of code? Think about what you're doing when you insert an item into the middle of a list, of an array. I'm sorry, I couldn't hear actually. I'm sorry?
Is that order n?
Yes, that's right. It's on because you have to move all the items after it over by 1 to make up. So that makes that a slow operation. So since you have to do that for every jar, you have to do that n times. So it's going to give your algorithm n squared complexity. Now there are some things you can do to speed up insertion, like use a linked list. But since we have a relatively small number of jars here, it just doesn't matter. This is going to run instantly, faster than a human can tell the difference. So since we're doing it for people to use and not as an API, that's fast enough. Yeah, so this is really good enough. We don't need anything faster, and this gives good output. And I will actually I will run the programs at the end and show everyone the output so you can see what that looks like. So it's getting a little loud in the back. You guys could quiet down. So let's think a little bit about this type of problem. Let's just step back to some theory and to some computer science for a second. We've got a criteria, in this case, even spacing, that we're trying to optimize for. And we don't want to get tired of eating any one thing. So what we care about most is the most common jars and keeping them equally spaced, which is what led us to this approximation that we came up with. I'm not making any argument that this algorithm is optimal, just that it works. It's good enough that you look at the list and you can't really see anything you would want to change to make it better. But our approximation is very specific. I wouldn't really know how to apply this algorithm I came up with to any problem other than something very, very much like spacing jars out on a shelf, which is really a little specific. We want some more general tool because we use computers to solve problems. We want a nice general tool like a programming language that can help us solve optimization problems in general. And even though our homegrown algorithm doesn't generalize well, there are algorithms that do, and we're going to talk about one of them. Does anybody want to guess from this picture which algorithm I'm going to talk about? And if you've seen this talk before, please don't answer.
Simulated annealing.
Yes, simulated annealing. That's right. Good call. So this is some metal being annealed. So annealing is basically heating a material, something like metal or glass, that doesn't have like necessarily a strong crystalline shape, something that you can heat, and when it gets hot, it will change structure. The internal structure will change. And the idea is to heat it up and then cool it back down in such a way that when you're done, the structure at the end is more uniform than it was when you start with. And it makes the material, metal or glass or whatever, easier to work with. And that's really what we want. We want metal that we can easily turn into something else, to some specific use. So that's the key part, is you're thinking about it makes the structure more uniform as it cools. So now that you're familiar with annealing as a general mechanical process, simulated annealing is exactly what it sounds like. You're literally just simulating this process of physical annealing. You're simulating the process of heating something way up and then gradually cooling it down so that the structure or the energy level becomes minimum, the structure becomes uniform. And you can apply this to any problem where you're trying to find an optimal point, a best case, because that's the same as the minimum energy level, the most uniform structure. So hopefully you can see this. The lines are a little thin and the contrast isn't great. But this is an animation from Wikipedia about simulated annealing. And basically, if you watch the temperature at the upper left, you'll see it starts out really high, and the red line showing what the structure is at this time is jumping around a lot. And the black line that zigzags across is a map of what the energy level is, the uniformity of that structure at various points. So higher actually means more uniform, lower energy. So as the temperature drops, the red line jumps around less and less, and it tends to get caught in these points of very low energy, very high uniformity. You can see early on it's jumping around a lot, but later on it jumps around less and less because there's less free energy to help it jump around between states, to help the structure of the cooling material change. And eventually you reach 0 and it settles down. Now in this picture, it settles down at the optimum point, at the very highest level of uniformity. That doesn't necessarily happen, but simulated annealing helps that happen by jumping around a lot, but tending to settle in the place of highest uniformity. And how fast you drop the temperature will sort of change, and what temperature you start at will change how likely you are to find an optimum and how long it takes and things like that. So think about our problem. This maps really nicely to simulated annealing, right? We want our jars to be literally spaced as uniformly as possible. It's exactly what we're trying to do. So if you think of these jars as particles in an amorphous solid like glass or metal, and each one of them has energy, and each one of them is pushing away from all the other jars, but especially pushing away from the jars of its same type. The red jars are pushing hardest against the other red jars. The blue jars are pushing against the other blue jars, but not quite as hard as the red ones, though, right? Because there's more red ones, so they're going to tend to be closer together. And then the green ones just sort of end up somewhere. So you're going to tend to have the red ones, because there's the highest stored energy, because there's the most of them, push each other the farthest apart out of all of them, followed by blue and followed by green. So you end up with a situation where your most common ones are most evenly spaced, which is exactly what we want. Another place that you might use simulated annealing, and this is a common thing in industry, or at least was, they may have more sophisticated techniques now, is in circuit board design. You have a couple of criteria you're trying to optimize. You want the board to be as small as possible, but you also want the traces on the board, the wires, to be as short as possible. So there may be some way that you can move the components all together and run all the wires around the outside, but the wires actually end up way longer than they need to be. So, and maybe if you made the board just a little bigger, you could fit all those wires in the inner parts of the board, and they wouldn't have to be as long. So simulated annealing is used to solve problems like that. You combine those two criteria together into one, just like when solving the knapsack problem, you can combine weight and value into a ratio, and you use simulated annealing to optimize it. So when I originally gave this talk, those were basically my examples of simulated annealing, and I wasn't super happy with them. So later, I saw a really cool example of simulated annealing on the internet, and I really encourage you to go check out this website after the talk. It's really cool. It's an image unshredder by Annealing. So the basic idea here is that it's going to shuffle up all of the columns, all of the vertical columns of pixels randomly, and then it's going to use annealing to randomly jump between states where those columns are in random assortments. But if two columns are very similar, they'll have very low energy next to each other, and they'll tend to stick together as they jump around. And so gradually, this picture will have bigger and bigger pieces that look like they're probably supposed to be columns next to each other, stick together until it starts to look again like the original picture. Excuse me. So rather than go into any more detail, I'm just going to play you a GIF. So you can see it randomly sorts them, and then it starts to wiggle them around. But now they're grouping together, they're clumping, and you're starting to see bigger and bigger sections of the original image emerge. And I had to play with the temperature, the starting temperature, and the rate at which the temperature drops quite a bit to get it to work this well. With the default settings, this particular picture basically didn't work. But it really shows how tweaking your parameters can cause an algorithm to work much better. I mean, where this ends up, a human could basically print this out, cut it into strips of paper, and then line them up exactly right to get that last bit. Or you could use some other algorithm, or start, instead of treating columns individually, treat each strip as a single column. Things like that. So this really gets you a lot of the way towards what looks like something completely random into getting a signal out of it, which is really cool. So I really, again, I'm going to show the URL one more time, nayuki.io. It's a really cool example of this. It's all done in JavaScript in the browser, so you can just look at the source code right there. I'll put it on Slack. And by I mean someone else. So again, I hate to be trite, but a great place to start to learn about this is Wikipedia. It's got a broad selection of examples. It's got a lot of cool links to words like meta-heuristic, which I know all of you want to understand, and gradient descent, another favorite of mine. So it's another optimization tool, like some of the approximation solving the knapsack problem that are really cool. So hopefully these examples reminded you that programming can be used to solve everyday problems, that some things you might run into around the house. It showed you how to problem solve and how to not be intimidated by something like this, and how to use computers to solve them in ways that are helpful. So real quick before I finish, I'm going to switch to the terminal, and I'm going to run these programs. But I'm almost done. I just want you to see that they run fast, and that they work. So I'm going to, I think, switch this mic off and shout, because I don't want to hold it. Am I loud enough? Yeah! Cool. Can people read that? No. How about now? Yeah. OK. So here is here's the actual imports at the top that I use in this program. So as you can see, I left the imports out. Yeah, I left the imports out so to make it fit into 20 lines, so I apologize for that. Also left out the return statement, but they're very simple. And then I just have the main function that just sets up the input, calls our approximation method, and then prints out the output. And I'll run it for you. So it prints out this list of maps listing which cuts to make from each board. So you can just grab each board of length 72 and make your cuts, and then grab each shorter board, then you grab each longer board, and then at the end you grab the shortest board and make that last cut. So this shows that no cuts are remaining. We use up almost all of our boards. And we're left pretty happy. So here you can see the other problem. We've got our pantry counts, and then our program, and then at the end I'm just going to print out the list of how things are ordered on the shelf. So you can see, right? Remember, our salsa verde was the one we had 20 jars of. That's at the very bottom, and then it's going to be every 6 to 7 jars from there up. So that's nicely evenly spaced. Whereas we get a much wider spacing of things like our tomatillo lime jam or our yellow tomato soup. So we have what, to the human eye at least, looks really evenly spaced output, both for common and uncommon jars here. So I don't know what all of these things are, but they all sound great. So yeah, that's all I have, and I'm glad to take questions. Yeah, Jordan.
So I have two questions. First of all, I haven't looked at simulated annealing, but can you, does that use MCMC to do the random walk, or how does it do that?
Does simulated annealing use MCMC to do the random walk? I know what simulated annealing is. I know what a random walk is. I don't know what MCMC is. Oh, no. That would be another method you can use. I don't know what the actual like pseudo-random selection algorithm looks like in most simulated annealing implementations. I think you could use a lot of different ones. Yeah, Jason.
So, to what extent have you learned about the theoretical side versus like the practical side of solving problems in constraints? So, for example, on the board cutting, like, you had some algorithm that predicted these things and chose the cuts. But what if, you're going to go make the cut and they say measure twice, cut once, and you actually cut, say, 2 inches shorter than what you expected? How would you have accounted for that?
How would you account for human error when you're designing algorithms, or human or whatever error, and make sure that you're resilient to that? Is that a fair way to state the question?
Yeah, perhaps.
Okay. I didn't account for that at all in these algorithms. I assumed that Jonathan is perfect and could do exactly what I had laid out for him. Yeah. In reality, right, you didn't have to be perfect in these. If he'd cut one 2 feet short, he would have said, oh, well, and made that piece out of 2 smaller pieces. And that's a lot of time how the real world works. Certainly that's how things work when we line up VMs and servers at the company I work at. Yeah. So I think that's the best answer I have. So any other questions? Anyone who hasn't been coming to ChiPy for 10 years? Anyone else? Sure. No, you can't get any jalapenos. All right, thanks everybody. Bye.